começou. Então, nós vamos dar início à defesa de trabalho de dissertação do Rafael Fontella Katopodis, que tem como título Reinforcement Learning with Weightless Neural Networks. And now I'm going to switch to English briefly, so that some people from our group, research group, can understand his presentation. And I thank the members of the reviewing board, Daniel Ratton Figueiredo from PESC-UFRJ, and Wouter Caarls from the Catholic University from Rio de Janeiro. I thank them very much for agreeing to participate in the Viva. So, Rafael, you can start.
Okay. Before I start, I would like to also thank Professor Daniel and Professor Wouter for accepting being part of this defense committee, and also thank everyone attending. All right, so the core theme of this work is reinforcement learning. And reinforcement learning, to put in really simple terms, is about learning-based methods to solve decision-making problems. And it has become, in recent years, one of the most popular topics in the overarching field of machine learning. And we can list a couple of reasons for this popularity. The first are the various impressive results that were obtained recently using reinforcement learning techniques, such as game playing at a level near or beyond what humans are capable of. But second reason for all the attention that reinforcement learning gets is that it seems to hold a lot of promise. And that's because several interesting and difficult problems can be thought of as decision-making ones, such as complex manipulation by robotic arms. It's one hard challenge that could be cast into this framework of sequential decision-making. And so reinforcement learning could possibly be the key to automating tasks like this. However, a big issue with the contemporary reinforcement learning algorithms is how computationally demanding they can be. And this is due in part to the use of deep neural networks and their high costs of training and deployment that can turn certain applications simply infeasible. Well, taking into account this issue, developing lighter weight alternatives becomes a really sought after goal. And in looking for these less demanding alternatives, weightless neural networks, also known as N-tuple nets, are promising candidates for the role. Because past works show that they can attain competitive results with other models, and they can do so using only a fraction of the computational resources. Unfortunately, we can't simply take these existing N-tuple systems and plug them into a reinforcement learning context. And the reason for that is that these networks were devised mostly to solve supervised learning problems. And doing so, they incorporate supervised learning assumptions into their algorithms that might not be valid assumptions in a reinforcement learning scenario. With this in mind, the goal of this dissertation was to understand what exactly stands in the way of using the existing weightless architectures in reinforcement learning, and to use that understanding in developing new N-tuple models that are suitable for the task of reinforcement learning. But before getting into these new models, I would like to go through some fundamental concepts first, starting with reinforcement learning. So we formalize the elements that make up a decision-making problem as a Markov decision process. And it's made up of two interacting elements, an agent and its environment. The agent influences its environment through an action signal, and in response, the environment produces a state and reward signals. And this interaction is going to give rise to a sequence of state, action, and reward random variables. And the values of these random variables will depend on the agent's behavior. We formalize the agent's behavior as a policy, which is a distribution of actions given the state where the agent finds itself. And we're interested in policies that are able to get high rewards in the long term. So to better quantify this objective, we define something known as a return, which is the discounted summation of rewards from a given time step onwards. So using the return, we can define a state value function as the expected return, given that we are in a state. And we can think of this function as a measure of how desirable it is for the agent to be in that state. And in a similar manner, we can define an action value function, which is how desirable it is for the agent to be in a state and then execute an action. The definitions we went through allow us to think about solving MDPs in a more concrete manner. So to solve an MDP, we have to find a good policy. And that is to say, find a policy that maximizes the values of the states, or approximately maximizes it. And one way we could try to do that is to directly search for a good policy, or alternatively, given this strong connection between policy and value function, we could go for a less direct approach, approximately maximizing the value function, and then extracting from it its corresponding behavior. These two ideas are the basis for the two major approaches in reinforcement learning, which are the value-based algorithms and the policy-based ones. All right, so in the value-based approaches, we want to obtain a good value function so that we can extract from it its corresponding policy. One theoretical result we can use here is the policy improvement theorem, which states that if we have a certain policy and its action value function, we can find a new policy by acting in a gradient manner in relation to the action value function. And what's remarkable about this theorem is that the new policy is as good as or better than the original policy. And we can turn this into a method for solving MDPs by building a sequence of policies, each one being an improved version of its predecessor. So we start with an arbitrary action value function. Then we extract an improved policy from it. Next, we estimate the action value function for this new policy. And then we repeat this process in an attempt to get policies that are ever closer to an optimal one. And this scheme is known as generalized policy iteration, or GPI. So this method has two main steps: the already mentioned policy improvement, but also an action value estimation. So how can we do that? Well, we can learn these estimates from experience using a learning model to represent the action value function. The most direct way we can do this is using a method known as multicolor evaluation, where we sample entire episodes. Then we compute the returns from each of these state action pairs visited. And finally, we use these returns as update targets for the model. However, one drawback of this choice of update target is that it requires sampling an entire episode before updating the model. One way we could do more frequent updating is by targeting not sample returns, but estimated ones. So we produce these estimated returns by bootstrapping. And a bootstrap return is made up of a few sample steps, and the remainder is approximated using the model itself. This allows us to perform more frequent updating, which could lead to faster learning, but it also introduces a bias, given that at each update step, we reinforce the current action value function, which could be a really bad action value function estimate. So there's a trade-off there that must be adjusted. Now, to finish this introductory part about reinforcement learning, let me quickly talk about the other major approach to solve MDPs, which is the policy-based approach, where we try to search for good policies directly without necessarily resorting to value functions. One way we can do this is by framing the problem as an optimization one. So we define a performance measure, and we iteratively update our model of the policy according to the gradients of this measure. And this is the idea behind policy gradient methods. For episodic MDPs, we can define the performance measure J as the value of the initial state of the episode. And now we're going to need to be able to compute the gradients of J. One of the most fundamental results in the theory of reinforcement learning is the policy gradient theorem that allows us to relate the gradient of this measure J to the gradient of the policy itself. But this equation for the gradient is not super useful because it involves quantities we don't know, such as the real action value function and this mu, which is the stationary distribution of states induced by the policy. But we can apply some transformations and put this into a more friendly form. And then we can sample from this expected value and use these samples as our gradient estimates in a stochastic gradient descent manner. And this is what is done in the famous reinforced algorithm. So both of the approaches in here, the value-based or the policy-based, rely on learning models, either to represent value functions or policies. And what we are interested in here is adopting n-tuple nets as models to these fundamental quantities in reinforcement learning. So let's talk about weightless neural networks. These neural nets, they differ from the classical concept of artificial neural networks by using memory elements as neurons. So they're not like the McCullough-Pitts neurons, where activations are based on the inner product between inputs and wave vectors. In these memory-based or RAN neurons, inputs are used to address a memory position, and the content of the addressed position is used as an activation signal. In its simplest form, we could have neurons with memory positions containing only a single bit. And when we present a training input, it addresses a position and sets it to 1. Later, when we present a task pattern to it, if the activation is 0, it means we are facing a novel input. Otherwise, if the activation is 1, it signifies that the pattern was seen during training. So this activation behavior means that RAN neurons can represent any Boolean mapping between inputs and outputs. But the downside is that they cannot generalize by themselves. So if a pattern wasn't seen during training, a neuron's output width will always be 0. But generalization can be obtained by organizing neurons into networks. And a common network architecture is the discriminator, where we encode inputs as binary patterns, and we have a number of RAN neurons, each observing only part of this pattern. When a pattern is presented to a discriminator, each of its neurons will produce an activation, and these activations are summed up into a number that is called the discriminator's response. And we can think of this response as a measure of how similar the input is to the training examples. Now, these weightless nets are commonly used in classification tasks, but they can also be used for regression. And one n-tuple net that is adequate for regression is the n-tuple regression network. It's very similar to the standard discriminator we just saw, but one of the differences is that a memory position stores not a single bit, but a pair of values. It stores a real value estimate and a counter. During training, we present a set of samples to the model, a sample consisting of an input x and a target value y. The sample input addresses positions. Then the target values are added to the estimates addressed, and the counters are incremented by 1 unit. And when using these models, the output is computed by summing the addressed estimates and then dividing by the sum of addressed counters. And one interesting fact about the n-tuple regression network is that it has a fundamental connection to kernel machines. We can show that with this particular update rule and output function, it implicitly realizes a Nader-Watson kernel regression. So weightless nets expect inputs to be binary patterns. And if our samples are not already in this format, we need to encode them as a binary pattern in some way. We consider 2 encoding schemes in this work, the thermometer encoding and the circular encoding. The thermometer works by having a binary pattern be more or less filled with 1s, depending on whether the value we want to encode is closer to the lower or higher end of the scale. So suppose we have the 0-10 interval, and we want to encode the value 4. The resulting pattern will have the first 2 bits active. And if we want to encode the value 8, it's going to be the first 4 bits that are active. Now, in the circular encoding, we always have about half of the bits active. And this block of bits is going to shift to the right proportionately to how close the value to be encoded is to the maximum of the scale. So when encoding the value 4, the block is going to shift twice. And when encoding 8, it shifts 4 times. It's important to note that we have to choose an encoding resolution. And this encoding resolution determines the number of bits in the binary pattern, and that also determines the number of possible distinct patterns. So if a resolution is too low, we are going to have a limited number of distinct patterns, and we might end up encoding 2 distinct values as the same pattern. And this is what happens here with the value 3, using this resolution of 5 bits. We end up mapping the same pattern as the value 4. Also, these encoding schemes are independent of whether we are trying to encode integers or real values. The only thing that matters is the relative position of these values in their scales. So if our interval was the 0, 1 interval and our values were 0.4 or 0.8, we would be able to encode them just as well. And the resulting binary patterns would even be the same ones, since the values maintain their relative positions in the scale. Okay, so now we can finally talk about putting these things together. We want to use n-tuple models to represent both value functions and policies. Value functions are real valued, so we need something that can approximate real value functions. And this is also going to be true when representing policies, which are distributions. We need a model that can approximate real or vector value functions. Given these requirements, we would think that the n-tuple regression network we just talked about would be a perfect choice. However, this model has some limitations. There are two big ones for the use we want to make here, both of them stemming from the assumptions made by Nadaraya-Watson regression, which is implicitly done by the network. The first one is an inflexibility in the objective function being optimized. So the Nadaraya-Watson regression is an approximation of this conditional expectation estimator. And this estimator is, in turn, the one that minimizes the mean square error. So this model is coupled to a specific loss function. And that's problematic if we wanted to use it for policy search, especially if we wanted to do policy search based on the policy gradient theorem. For that, we would need to be able to specify the loss function and also be able to use gradient information. We're going to talk more about this issue later. The second limitation is the one we are going to focus first, and it's also related to this conditional expectation, in that it assumes all inputs and target values were drawn from a fixed distribution. In other words, a stationary distribution. This is something that might make sense in certain supervised learning scenarios, but not in reinforcement learning. So the way learning progresses in reinforcement learning necessarily makes the distributions involved shift as time passes. And why is that? Well, when we start training our agent, more often than not, it's going to visit poor states and select bad actions. But as it gains evidence that being in other states and performing other actions is more rewarding, the distribution of those quantities is going to change. However, a stationarity assumption works against that. To illustrate how this assumption can be detrimental, we have a really simple density estimation problem here. So the solid line represents the true underlying distribution, and the dashed line is the prediction made by a model that assumes stationarity. And in each of the figures, the model receives a new batch of samples drawn from the distribution and learns from it, but it doesn't learn from scratch. It still carries over what it learned previously. However, the true distribution is changing over time. So the result is that the model diverges more and more from reality. And that's because it attributes the same weight to all samples. It's as if it's incapable of forgetting the past in a scenario where it would benefit from doing so because the distribution is changing. Well, we can use this understanding to create a modified version of the n-tuple regression network, one that enforces the forgetting of older samples. We introduce a forgetting factor, phi, defined in the 0, 1 interval, and the difference is going to be in the update rule and output function of the model. So in the original update rule, we just accumulated the target values of all inputs that address the same position in the neuron. But in the new update rule, we're going to first multiply the current value of the memory position by the forgetting factor, and then we are going to accumulate a new target. And the update of the counter stays the same. And the intuition here is that at every time we receive a new observation, the contribution of past observations decays. So in the original n-tuple regression network, all samples that addressed a certain position were simply summed up, which means that they contributed equally to the content of that position. But with this new learning rule, we are attributing weights to the samples. And we're doing this in a way that their contributions are proportional to how recent they were seen. Since we are trying to attribute these different importances to the observations, the output function can stay like this as a simple average. This denominator can't be the sum of counters. It needs to be the sum of weights. So how should we get this sum of weights? Well, we are not storing these weights anywhere, but we don't really have to. because the weights come from a geometric progression. So we can simply compute the sum using the formula for the first terms of a geometric series. Going back to our illustration of the challenge of non-stationarity using a density estimation problem, we can see that the model becomes more capable of tracking the underlying distribution when we make use of a forgetting factor. Now that we have a version of the n-tuple regression network that is able to handle non-stationarities, we can use it to approximate action value functions in a generalized policy iteration fashion, as in the SARSA algorithm. To give a rough sketch of the algorithm, we start collecting some experiences by having our agent interact with the environment. We don't have an explicit policy, so we select actions by querying the action value model. Then once we collected a certain number of steps, we can start computing estimated returns using the collected rewards and the model itself. And here I'm using F to denote the output of the model. And notice that we have to encode the state as a binary pattern before using it as an input. And once we have a return, we can use it as an update target for the model. And then we repeat this process for a number of episodes. With this description, I'm leaving quite a few details out. I didn't think I should put a full pseudocode block in the slide, but there are two details I really should comment on. Starting with using the forgetting n-tuple regression network to represent an action value function. An action value function has two inputs, a state and an action, but an n-tuple net expects a single binary pattern. So how do we reconcile this? Well, the simple solution is to have the model take as input only the state, encoded, that is, and output the values for all possible actions. And we can do this in two ways. Either we have a single discriminator that stores vectors of values, or we have one discriminator for each possible action, each of them storing only real values. I've used the first option, but they should be equivalent. The last thing I should comment about this algorithm is the action selection process. So we don't have an explicit policy. We use our action value model to select actions. And the idea here is that when the agent is in a certain state, it selects an action by giving that state to the model, receiving back the value estimates of all possible actions, and selecting the one that seems most promising. But the problem with this idea is that we are trusting our model completely and all the time. But our model could be really bad, especially at the earlier stages of training. So always following this poor model would keep the agent trapped in a subset of the space of states and away from the most crucial states, which are the ones that show to us that we could be doing better. To combat this, we use a really common strategy in reinforcement learning called epsilon greedy. And what this means is that most of the time we select actions according to the action value model, but sometimes with a small probability, we select one action randomly. And this is done in an attempt to have the agent explore more of the space of states. Okay, so that was our approach to modeling action value functions with an n-tuple net. Now, what about approximating policies? So the addition of a forgetting factor in the n-tuple regression network was a simple way to make it better operate under non-stationarities, but it does not solve the first issue we noted. It still optimizes an implicit error measure, and there's no way for us to select and optimize a different loss function, like in gradient-based methods. So we can't make use of the policy gradient theorem to do policy search using this forgetting n-tuple net. To get around this issue, we went back to the connection between n-tuple nets and kernel machines, and we attempted to devise a network based on a different kernel method, one that makes different assumptions. So kernel machines are models of this form, a weighted summation of basis functions, and they are generally used in batch learning settings, so where all data is known beforehand, and it all comes from the same distribution. But it turns out we can also create kernel models in an incremental way, much like gradient descent. So we are used to gradient descent with parametric models, right? And we can understand it as a tool that helps us navigate in a space of possible parameter vectors. So at each gradient step leads us to a new point in this space, to a new possible parameter vector for the model. And we are looking for good vectors of parameters, one that minimizes a loss function. Well, we can bring this idea to learning with kernels. So instead of navigating through a space of parameter vectors, we want to navigate through a space of kernel models. In this kernel space, each point is a kernel model. So we start with an empty kernel model. It's always 0. And we're going to do a gradient step by getting a first sample, x1, y1, and computing the gradient of the loss. And then we're going to append a new basis function to the model. And this basis function is going to be centered over the sample, x1, and weighted by the gradient of the loss. And when we append this basis function, we are effectively navigating to a new point in space. So this weighted basis is what we are calling the functional gradient of the model at this point of training. And we are going to repeat this process for each new sample. And this is the intuition behind the functional gradient descent method. So we drew inspiration from this functional gradient descent and devised a new n-tuple net. It has a lot in common with the n-tuple regression network. It's also organized as a discriminator with a number of neurons, but each memory position stores only a value estimate and or a pair of values. The update rule of the model is where this idea of functional gradient descent is used. So for a given input, xt, one memory position is accessed in each of the neurons, and the content of these positions are updated with a gradient step for a chosen loss function. When we present a test input to the model, its output is computed simply by adding up the values addressed in each of the neurons and then dividing by the number of neurons. And just as with the n-tuple regression network, this model also behaves as a kernel machine, but one learned using functional gradient descent instead of the Nadaraya-Watson regression. We provide a proof for that in the text. So this is an n-tuple system that admits being trained in a gradient descent manner, which makes it possible for us to use it in policy search. To use these networks as policies, we need to ensure that they behave as distributions. And the easiest way to do this is by using the output of the network to parameterize a family of distributions. And we can choose a distribution depending on the action space of the reinforcement aligning task. So if we are dealing with only 2 actions, for instance, our policy could be based on the sigmoid function. If our action space is discrete and finite, we could have a policy based on the softmax function. And finally, if our action space is continuous, possibly multidimensional, our policy could be built around the normal distribution, with the output of the network determining the mean vector of the distribution and the covariance matrix being fixed. And the way we use this functional n-tuple net for policy search was an adaptive version of the reinforced algorithm. So we collect an entire episode by having the agent interact with the environment. The actions are selected by sampling from the policy parameterized by the network. Once we have an entire episode, we compute returns. And then we use these returns to compute the gradients. And the cycle is repeated for a number of episodes. We can also use the 2 networks we introduced, the functional n-tuple net and the forgetting n-tuple net, together in the network critic algorithm. So we train 2 models, an approximation of a policy using a functional n-tuple net, and an approximation of a state value function using a forgetting n-tuple net. And this is still a policy search algorithm. It's very similar to the one in the previous slide. One of the differences is that we use estimated returns instead of full episodic returns, sorry. This is only possible because we are training a state value function model. And this allows us to make more frequent updating and not have to wait full episodes. Another difference here is that instead of using the return in the policy gradient calculation, we use the difference between the return and the state value given by the state value model. This difference is called an advantage. And we use this advantage expecting it to have a lower variance than the returns, which could possibly lead to a more stable learning. Other than that, the 2 networks are updated just as in the previous algorithms. Okay, now for some experiments. We tested these 2 approaches in a few simulated control tasks. They vary in their action spaces and in how challenging they are. The first one is the simplest, car pole, where the agent must keep the pole upright by moving the car to the left or to the right. The action space here is binary. The second one is lunar lander with a discrete action space. The agent must control the rocket to land on this pad, and it does so by activating or deactivating its thrusters. The third task is mountain car, where the agent must drive up to the flag, but it's not strong enough to get there directly, so it must learn to go back and forth to get momentum. And the action space here is continuous. The agent controls the force that is applied to the car. And the last one is hopper. It's a kind of a simplified robot, and it's a bit more challenging than the other ones. It also has a continuous action space, but it's a multi-dimensional one. The agent controls the torques that are applied to the 3 joints of the robot. And the agent is rewarded by first not letting the robot fall and by moving it forward. And given its physical characteristics, it only has a single leg. It can only move forward by learning a sort of a hopping gait, hence its name. The first set of experiments we did were intended to assess how the different hyperparameters of the n-tuple models we proposed influence learning. So we start with the forgetting n-tuple sarsa and the encoding resolution n-tuple size hyperparameters. And these were the results for carpal. So the curves here and in the next slides are average learning curves. So we ran the algorithm multiple times with different random seeds and averaged the results in an attempt to get a sense of the expected behavior. And we also apply a moving average to better highlight the trends in the curves. And the main takeaways are that we could only get the best results in the 2 higher resolutions, which is easy to understand. The lower resolutions are probably losing too much information, and we are probably having relevant states that are being mapped together into a single binary pattern. But there are diminishing returns in increasing the resolution. So we can barely notice a difference between the 64 and 128 bits of resolution. More interestingly is how the tuple size interact with the resolution. So for instance, with a 16-bit resolution, the tuple size of 64 was the worst performer, while in the 2 higher resolutions, this tuple size was the best one. And this is due to the fact that the tuple size and encoding resolution, they jointly determine the number of neurons in the discriminators. And this is in a trade-off between model complexity and generalization. So if the tuple size is too big relative to the encoding resolution, the number of neurons is going to be too small, and the model won't be able to generalize properly. But on the other hand, if the tuple size is too small relative to the encoding resolution, we are going to have a large number of neurons, but they're going to be limited ones because each one is observing only a small part of the input. So they might end up blind to important correlations. The same observations can be made for the lunar lander experiment, with the best results being with the higher resolutions, but we have diminishing returns in increasing the resolution. And we can also see the trade-off between complexity and generalization. So the agents that do best here are the ones that don't have too big or too small a tuple size relative to the encoding resolution. Something else we tested was the choice of encoding scheme. So what are the differences between using the simple thermometer or the circular encoder? And these are the results. So for both carpal and lunar lander, the circular encoding led to better results. And this is quite pronounced in the lunar lander case. And we think this might be due to the fact that both tasks are, in a sense, regulation problems. So where the control signal should be chosen with the goal of bringing the state close to a set point. In problems like this, states that are close to the set point are similarly of high value, while extreme states, ones that are far from the set point, are similarly of low value. In the case of carpal, for instance, we could think that the set point is having the card close to the center of the screen, not moving, and with the pole upright. So states that are close to this one are similarly of high value, while states where the card is far from the center or moving too fast are going to be similarly of low value. So the symmetrical nature of the circular encoding might be helping here. For the last experiment with the forgetting n-tuple nets, we tested the forgetting factor. And the results serve to show the importance of using it, but also that it requires some fine-tuning. The curves in purple are the ones using a factor of 1. which actually means no forgetting at all. The model is going to behave just as the original n-tuple regression network. And as expected, with no forgetting, the model gets stuck at a level really far from optimal, because the bad value estimates from earlier in training still have a lot of influence in the model, even in the later stages of training. So here, some forgetting was essential. All other values of forgetting helped in some way in comparison with this baseline, but too low a value for the factor also doesn't perform too well. And that makes sense because we're forgetting too much. We're not allowing the agent to accumulate experience. We did the same experiments with the n-tuple policy gradient approach. So for these experiments, we used the two tasks with continuous action spaces, that is mountain car and hopper. Starting with the resolution and tuple size. Mountain car is a bit different than carpool and lunar lander because good results were reached even with the lowest resolution. Here, a cumulative reward above 50 corresponds to an agent that is able to reach the flag. And even in the lowest resolution, we have agents that reached a reward above 50. So resolution didn't seem too much of a problem in this task. And in terms of the tuple size, even in the lowest resolutions, the best agents were the ones that used the large tuples. So the trade-off between complexity and generalization seems to be leaning towards complexity in this task. The agents that are doing best here are the ones with not too many neurons, with a small number of neurons. In Hopper, the picture is a bit different. Learning is considerably slower and noisier, and this is because the task is a bit more complicated than the other three. Something else we tested, something else that I have to point out here, sorry, is that the best results that were reached, these ones around 500 and 600, they correspond to agents that learn to stand upright, but not to hop, at least not hop consistently. So they ended up in a local optima. Increasing the encoding resolution does seem to improve performance a little bit. And the best results were attained with the smaller tuple sizes. Now, for the encoding scheme, unlike what we saw with carpool and lunar lander, here we don't see much of a difference between the encoding schemes. And this might be because mountain car and hopper can't really be seen as regulation problems. In mountain car, for instance, we could think that the position of the flag could be regarded as a set point, but an agent only succeeds in reaching the flag by first learning to move away from it to gain momentum. Finally, we have the learning rate, hyperparameter that the forgetting n-tuple network didn't have, and it affects learning in a really predictable manner. Small learning rates lead to slow learning or even no learning at all, and large learning rates can diverge completely. So good learning rates must be found somewhere in the middle. To get a sense of how these agents are doing and not just judged by learning curves, here are some recordings of these agents in action, that is after training. So the first two, carpool and lunar lander, are using n-tuple sarsa agents. And the other two, mountain car and hopper, are using n-tuple reinforce agents. By now, we've seen that the n-tuple based algorithms are able to learn successful behaviors, but how do they fare against models that are more commonly adopted reinforcement learning? So to make this comparison, we also trained multi-layer perceptron-based agents using pretty much the same algorithms I showed, the value-based one and the policy-based one, but replacing the weightless neural nets by MLPs. About the architectures of these MLPs. All of them had the same number of hidden layers and same number of units in each hidden layer and same activation functions. They only differed on their output, depending on whether they were being used to approximate a value function or a policy. So for value functions, the output is a vector with size that is equal to the number of possible actions. And in the case of policies, they also differ depending on the action space. So if the space is binary, the network outputs a single probability to parameterize a Bernoulli distribution. If the space is discrete, the output goes through a softmax function. And if the space is continuous, the output is a vector to be used as the mean of the normal distribution. We ran each combination of algorithm and control task 10 times with different seeds. And then we took note of the average cumulative reward in the last episode by the end of training. And these were the results. So, okay, what are the takeaways here? Well, the main one is that the versions of the algorithms that used n-tuple nets are able to keep up with the MOP ones. In Carpool, for example, the n-tuple agents did a little bit better. In Lunar Lander, the MOP agents came ahead by a bit. In Mountain Car, it's interesting. The MOP variants got stuck in a local optima, which didn't happen in the n-tuple versions. And in Hopper, the n-tuple methods also got higher cumulative rewards. But again, I have to point out that unfortunately, none of these agents learned to hop. So I wouldn't count this one as a big win for the n-tuple nets. Okay, in closing, we tackled the problem of using weightless nets to approximate value functions and policies in problems of reinforcement learning. And to do so, we proposed two modified learning models, given that the existing ones don't adapt too well to the challenges imposed by reinforcement learning. The first one used a kind of a forgetting process to better handle non-stationarities when approximating value functions. And the second is an n-tuple net that can learn using gradients. And that was inspired by the idea of functional gradient descent in kernel models. We evaluated these approaches in simulated control problems, first studying how the main hyperparameters influence learning, and then comparing it to MOP-based approaches. Now, in terms of future work, on the algorithmic side of things, in particular related to the policy gradient approach, it would be interesting to adopt more sophisticated gradient methods, such as the ones based on natural gradients or ones that add divergence constraints, because these are the kind of techniques that are used in some of the state-of-the-art methods in reinforcement learning. And on the experimental side of things, I think it's important to have a more extensive comparison between the n-tuple and MOP-based approaches, especially in terms of resource usage. All right, let's see. Thank you.
Thank you, Rafael. You presented your work in 41 minutes. Congratulations. And I am going to interrupt this recording and switch back to Portuguese for the examiners to question you. So just interrupt this recording.